This is Dr. Clark, and in this video we're going to learn how to do triple integrals using cylindrical coordinates. Let's get started. So the first thing we need to do in cylindrical coordinates is talk about what are cylindrical coordinates themselves. So we're in 3 dimensions, so we're in R3, and you've got some point in space, which normally you would think of as x, y, z, the x, y, and z coordinate. But what we're going to do is just use polar coordinates in the xy plane and then the z coordinate as usual. So given a point up in space, you can think of where's that point down in the xy plane, use theta and r, so regular polar coordinates to specify that, and then up to the z coordinate, just like so. A couple ideas that are worth knowing. If you set r equal to constant, you get a cylinder in polar coordinate or in cylindrical coordinates. So this is one reason why they're called cylindrical coordinates, is because a constant r value generates a cylinder. And if you set z equal to r, you would get a cone. And so one way to think of this is z equals r should be like a line. If you did, well, for example, z equals y would be a line, or z equals x would be a line. But z equals r just gives you that same line, but for every possible r value. So as the radius goes out, the thing goes up. And if you had z equals 2r, you'd have a steeper cone. Z equals 1/2 r, you'd have a smaller cone. And if you had a particular angle you wanted, if you wanted this to be a particular angle, you can use trigonometry to figure out what the right slope would be to get that angle. So when we start doing integration using cylindrical coordinates, what we typically do is think of the z coordinate as being bounded below and above by 2 functions g and h, which depend on the polar coordinates. Okay, so this is the bottom and top. And then in polar coordinates, you think of the thetas being controlled by 2 particular angles, and the radiuses being controlled by some function of those angles. So typically what happens is you have the angles go between here and here. The r values are controlled by the angles, so it could be 0 to 5 or something if it was the inside of a circle, or it could be some other function of theta if it was a cardioid or something like that. And then the z coordinates are just bottom and top, controlled by 2 functions that are controlled by the cylindrical coordinates. What you see here is dv, the volume element, should be a small little cube of space, but in cylindrical coordinates what you end up with is this this expression here, r dz dr d theta. Remember, in polar coordinates, r dr d theta gave you a small patch of area. Multiplying that by dz gives you a small patch of volume, so that's dv. And then if you have some function, you can weight each one of those volumes and then add them all up using the integrals. This is what that looks like in 3 dimensions. There's this little dA down here. This r dr d theta gives you that area. Multiplying by z gives you a small patch of volume, and then adding up all of those volumes for the entire region would give you the total volume. This would be another example of how it might look in an integral. If you started with the triple integral, you can actually think of it in terms of splitting it, into the bottom and top function, u and v, giving you what are we doing on top, what are we doing on the bottom, and then over some region d, which could be written dA here, but now we can just replace that d with this region d represented in polar coordinates, which would give you the r dr d theta at the end, and that's how you get dz dr d theta with the r dz dr d theta. All right. So one advantage of cylindrical coordinates is it can take messy expressions and make them a little bit cleaner. In particular, all of the bounds might be numbers, which might make the integrals easier to do. Hopefully that is helpful to you, and in the next video we'll do some examples. And yeah, cylindrical coordinates, not too tough if you know your polar coordinates. Should be pretty straightforward to upgrade triple integrals into cylindrical coordinates.